All right, let's kick things off with something super relatable. You know that moment you pull clothes out of the dryer and they're all like stubbornly stuck together, almost hugging?
Oh, yeah, static cling,
Yeah.
definitely.
Or when you reach for a car door and zap, that tiny unexpected shock.
Happens all the time, especially in dry weather.
Yeah, my personal favorite,
Mm-hmm.
rubbing a party balloon on your hair and then it just sticks to the wall
Mm-hmm.
like magic.
Uh-huh. Defying gravity, seemingly.
Totally. Kid, I used to shuffle my feet on the carpet just to zap my brother. Never really thought it was, a deep dive into physics back then.
Yeah, right. Little did you know.
Exactly.
Hmm.
But these aren't just quirky little nuisances or parlor tricks, are they?
Not at all.
They're actually fascinating everyday glimpses into a powerful, invisible force that's constantly at play around us.
Mm-hmm.
And today, we're diving headfirst into that force, electrostatics.
That's right. And at its heart, electrostatics is really the study of electrical phenomena when electric charges are, well, for the most part, at rest.
At rest. So not like the electricity flowing through wires.
Exactly. It's distinct from electrokinetics, which involves moving charges, like in an electric circuit. Here, we're focused on the forces and interactions of charges that have sort of accumulated and are essentially still.
Okay, so our mission today is to really get to grips with how these still electric phenomena work. We're going to use your excellent research to explore the very nature of electric charge itself.
Right.
And then we'll reveal the fundamental law that governs these invisible yet incredibly strong forces.
Sounds like a plan.
Get ready for some aha moments, because this stuff truly underpins so much of our physical world.
It really does.
Okay, let's unpack this then. When we talk about these everyday examples, the balloon, the car door, the static cling, even charges building up in clouds before lightning strikes, what's actually going on at a fundamental level?
Well, what's fascinating here is that all these scenarios are instances of charge transfer and accumulation.
Transfer and accumulate.
All right. Basically, charges get moved from one object to another, and then they tend to remain relatively at rest on that object.
Hence the statics part.
Precisely. Think about the party balloon again. When you rub it on your hair, friction causes electrons, these tiny charge carriers we'll definitely talk more about, to literally jump from your hair onto the balloon.
Okay, so the balloon gets extra electrons.
Exactly. Those excess negative charges then stay on the balloon's surface, creating an imbalance. And that imbalance allows it to, say, stick to a neutral wall through induced charges.
Induced charges.
Right.
Interesting. And the dryer. Same idea.
Same basic principle. Clothes tumbling around, rubbing against each other, that friction moves charges around. Some clothes end up with extra electrons, some lose them.
Leading to attraction
Mm.
or repulsion.
Mm.
Static cling.
You got it. And even lightning, that huge spectacle, starts the same way. Charges building up in clouds, mainly due to friction between tiny ice crystals and water droplets moving around up there.
Wow, so it scales up massively.
It does. But in every case, these newly distributed resting charges then create forces and interact with their surroundings, sometimes subtly, sometimes dramatically.
So it really does all come down to these charges. We clearly experience their effects, but what are these charges fundamentally, and how do they behave?
Okay, so in nature, we primarily deal with two fundamental types of electric charges. Positive and negative.
Positive and negative.
Now, the names positive and negative are actually kind of arbitrary. Ben Franklin chose them, but we could have called them up and down or A and B.
Huh, really?
Yeah, but their behavior is universal and totally consistent. And the core principle is beautifully simple. Charges of opposite signs attract each other. They pull together.
Okay, positive attracts negative.
Right, and charges of the same sign repel each other. They push apart.
So positive repels positive, negative repels negative.
Exactly. That's the fundamental rule of interaction, attraction and repulsion based on sign.
Now, here's a concept that really changed my perspective when I first encountered it. Quantized charge. If we zoom in even further, what exactly does quantized mean in this context? Does it mean charge isn't like continuous?
That's a really crucial insight, and you've nailed it. Electric charge is quantized.
Okay.
Which means it doesn't exist in just any arbitrary amount like pouring water. It only comes in discrete, fixed quantities.
Like steps on a staircase, not a smooth ramp.
That's a great analogy. Or think of it like Lego bricks. You can have 1 brick, 2 bricks, 100 bricks, but you can't have 1.5 bricks.
Right, no fractions of a brick.
Exactly. The same applies to charge. It's always an integer multiple of a fundamental unit. We call this the elementary charge.
The elementary charge. The basic building block.
Precisely. And for free particles, things that exist on their own, you simply won't find fractions of this charge. ever. No half charges or quarter charges floating around.
So even in, like, giant particle accelerators smashing things together, they wouldn't expect to find a fraction of this elementary charge. That's kind of wild.
It is wild, but that's what all evidence points to. It's a fundamental property of nature. And we even have a precise value for this elementary charge. We usually denote it as E.
Yeah.
And its value is incredibly tiny. 1.602 times 10 to the power of minus 19 coulombs.
Wow, 10 to the minus 19, that's vanishingly small.
Almost impossible to picture, right. But that's the fundamental packet of charge. So the total charge of any object, which we usually represent with the letter Q, can always be expressed as Q equals plus or minus n times E.
Where n is?
N is always a whole number, an integer. 1, 2, 3, a million. It just tells you how many elementary charges are present, either in excess or deficit, and whether they're positive or negative overall.
Okay, that makes sense. Quantized, integer multiples of E. So if these elementary charges are our fundamental building blocks, where do they typically live? What's their home base in the world of matter?
Right, good question. To understand that, we need to zoom into the structure of matter itself, down to the atom.
The atom, smallest unit of an element.
Exactly. Atoms consist of a really dense, massive nucleus right at the center, and this nucleus is made up of protons and neutrons.
Protons and neutrons.
And then, orbiting around this nucleus are much, much lighter particles called electrons.
Okay, let's break those down. Protons.
Protons are found in the nucleus, and they carry a positive elementary charge, so plus E. They're also quite massive on this scale, about 1.672 times 10 to the minus 27 kilograms.
Okay, positive charge in the nucleus. Got it. Neutrons.
Also in the nucleus, and as their name kind of suggests, neutrons are electrically neutral, no charge at all.
Neutral. Makes sense.
Their mass is very, very similar to protons. It's just slightly heavier, actually, around 1.675 times 10 to the minus 27 kilograms.
Almost identical mass to protons, but no charge.
Yeah.
And electrons.
Electrons are the ones orbiting the nucleus, and they carry a negative elementary charge, E.
So the exact opposite charge of a proton.
Exactly the same magnitude, just the opposite sign. But here's the kicker. Their mass. It's tiny. Only about 9.11 times 10 to the minus 31 kilograms.
Whoa, wait. Minus 31 compared to minus 27 for protons and neutrons.
Yep. That means an electron is about 2,000 times less massive than a proton or a neutron.
Wow. So electrons are incredibly tiny in mass, but they pack the same electrical punch just negatively as a proton. That's fascinating.
It really is.
But if they're so incredibly light and moving around, what holds them in orbit around the much heavier nucleus? Why don't they just, like, fly off?
Ah, excellent question. And the answer brings us right back to our main topic.
Electrostatics.
Exactly. The electrons are kept in orbit precisely by the electrostatic force of attraction between the negatively charged electrons and the positively charged protons in the nucleus.
Ah, the opposites attract rule again.
That's the one. This constant attractive force acts as the centripetal force, always pulling the electrons inward, keeping them bound to the atom.
So the electrical force is what holds atoms together, basically.
Fundamentally, yes.
Yeah.
And in a neutral atom, the number of electrons orbiting equals the number of protons in the nucleus. Their charges cancel out perfectly, giving a net charge of 0.
Balanced. Stable.
Right. And this balance is key to the stability of most matter around us. Of course, when you gain or lose electrons, you disrupt that balance.
You get ions, charged atoms.
Exactly. Which drives all of chemistry, really. And changing neutrons gives you isotopes. But that's more about mass and nuclear properties, not charge.
What an incredible journey, just digging into the atom. So from quantized charges to this dance of protons, neutrons, and electrons, we're building a picture. But what about the strength of these forces? We know opposites attract, likes repel. But how strong is that push or pull? How do we actually put a number on it?
Right. To quantify this force, we need to talk about the brilliant work of Charles Augustin Coulomb.
Coulomb. Sounds familiar. French physicist.
That's him. Lived in the 18th century, born 1736. He conducted really groundbreaking experiments to measure this electric force very precisely.
How did he even measure such a tiny force back then?
He actually developed his own incredibly sensitive device called a torsion balance. It allowed him to measure the very slight twisting caused by the repulsive or attractive forces between small charged spheres. Really meticulous work.
A torsion balance.
Yeah.
Wow. Okay, so what did his experiments reveal? How did he figure out the rule?
His work led directly to what we now call Coulomb's law. It's an equation that elegantly describes the magnitude of the electric force between 2-point charges.
Okay, lay it on us. What's the formula?
The formula is F sub E equals K times the absolute value of Q1 times Q2, all divided by R squared.
All right, let's break that down. F sub E, that's the electric force.
Yep, the magnitude of the force, how strong it is.
Okay.
K is Coulomb's constant. It's a universal proportionality constant, and it has a value of about 9 times 10 to the power of 9 Newton meters squared per Coulomb squared.
9 billion.
Ah.
That sounds like a big number.
It is. It tells you the electrostatic force is inherently very strong, much stronger than gravity at the atomic scale.
Okay, then Q1 and Q2.
Those are the magnitudes of the two charges involved. Importantly, we use the absolute values here.
Absolute values. Why?
Because the formula calculates the strength or magnitude of the force. The actual signs of Q1 and Q2, whether they're positive or negative, just tell us the direction. Are they attracting or repelling?
Ah, okay. Formula gives strength, signs give direction. Makes sense.
And then?
And finally, R squared in the denominator.
R is the distance between the centers of the two charges, and it's squared. That's crucial.
Okay, so what does this formula tell us overall? What are the key relationships?
Well, two main things. First, the force is directly proportional to the product of the magnitudes of the charges. More charge means more force. Double one charge, you double the force. Double both, you quadruple the force.
Okay, proportional to charge. Makes sense.
But second, and this is really important, the force is inversely proportional to the square of the distance between the charges.
Inverse square, right? So if I double the distance between two charges, the force doesn't just get cut in half. It becomes 1/4 of what it was.
Exactly. It drops off much faster than you might intuitively think. Triple the distance, the force becomes 1/9.
Wow. That's a huge drop-off, a really powerful effect of distance, like turning down the volume, but it gets quiet way faster.
Absolutely. That inverse square relationship means distance has a dramatic impact. Small changes in separation can lead to really significant changes in force.
Which explains why static cling feels strong up close, but doesn't, pull socks together from across the room.
Precisely. The force weakens very rapidly with distance, but don't let that fool you about its intrinsic strength.
How so?
Well, compared to gravity, even between tiny particles like protons and electrons, the electrostatic force is enormously stronger than the gravitational force between them, like orders and orders of magnitude stronger.
Really? That much stronger?
Oh, yeah.
That puts it in perspective.
Yeah. And one more point about Coulomb's law. It respects Newton's third law. The force that charge Q1 exerts on Q2 is exactly equal in magnitude, but opposite in direction to the force that Q2 exerts on Q1.
A Q reaction. Even with invisible electric forces.
Always. Physics is consistent.
Where else do we see electrostatics popping up in our modern world? Things maybe we don't immediately recognize.
Oh, it's everywhere once you start looking. Think about photocopiers and laser printers.
Okay. How do they use it?
They use electrostatics to place the ink powder, precisely onto the paper. Basically, a drum inside is given an electric charge pattern that matches the image you want to print.
Like an invisible electric stencil.
Sort of. Then, charged toner particles are attracted only to the charged parts of the drum. They stick there like the balloon to the wall, but with incredible precision.
And then transferred to paper. Clever.
Very clever. Or think about electrostatic painting, especially for cars.
Right, I've heard of that. How does it work?
The paint particles are given an electric charge, and the car body is given the opposite charge.
Opposites attract again.
Exactly. The paint is strongly drawn to the metal, creating a super even coat, even wrapping around corners and edges. It minimizes overspray and waste. Really efficient.
That makes perfect sense. Using the force to guide the paint. So next time you hear that crackle from your clothes coming out of the dryer, or you feel that little tingle of static, let me take a second.
Yeah.
Consider those billions upon billions of tiny charges at play, silently at rest for a moment, but capable of immense force, shaping everything from the smallest atom right up to the grandest lightning storm. It makes you wonder, doesn't it? What other invisible forces in our world might you start looking at differently after today's deep dive?